So we'll record. There we go. Okay. So verifying trig identities, section 6.1. So we're going to go through some of the fundamental identities, and we're going to talk about what an identity is. And then we're going to use some of these fundamental identities, which you are already familiar with, some of them, in order to simplify trig expressions. So complicated trig expressions, we're going to make less complicated by replacing different parts of the expression with these identities to make them much simpler and easier to look at. We're not really doing anything with them right now, so we're just gonna make them as simple as possible. That's going to be practice for leading up to verifying trig identities. And when we're verifying trig identities, you're basically given an equation and you're told the left-hand side the left-hand side is equal to the right-hand side, even though they might look very, very different. And your job is to prove that the left-hand side is equal to the right-hand side. And we'll talk about the rules around verifying the trig identities. Now, the reason that we talk about trig identities is next year in calculus and beyond, it can oftentimes be helpful to rewrite a complicated trig function or a complicated trig equation in order to work with it. So in order to differentiate, to integrate, to solve an equation, it can be helpful to simplify by being able to rewrite using these fundamental identities. And the fundamental identities are going to be identities that you should just be familiar with. And we're not talking about all of them in 6.1. We're going to kind of introduce some more as we go in 6.2, 6.3, 6.4. I'm going to tell you the ones that you need to memorize, okay? And I will tell you the ones that I will give you. And I have communicated with Mr. Green, who teaches AP Calc AB, on the identities that he expects you to know and that the AP exam expects you to know. So you'll have to memorize those ones, and then there's other ones that are kind of you'll be given along the way. Okay, so an identity. An identity is an equation that is true for all values of the variable for which the expressions in the equation are defined. If an equation is true for only some values of their variable, then it's a conditional equation. So you can think of like a conditional equation, like when you solve a linear equation and you have one solution, or if you solve a polynomial, like a second degree polynomial equation, also known as a quadratic equation, and there's maybe two solutions or one solution. Those are conditional equations when there's only sometimes a value that will make this statement true, make the left-hand side equal to the right-hand side. So an identity is when all values within the domain will make the left-hand side equal to the right-hand side. You know this first set of identities already. So this should be easy. This is already in your memory. These are known as the reciprocal identities. So the fact that cosecant is the reciprocal of sine, right? So cosecant is equal to 1 over sine. Secant equals to 1 over cosine. Cotangent equals to 1 over tangent. We can also flip those. And we can say, okay, well, sine is equal to 1 over cosecant. And cosine is equal to 1 over secant. And tangent is equal to 1 over tangent. These are the three reciprocal identities, though, that like if I were to ask you what the reciprocal identities are, these are the ones that I'm looking for. You are also already familiar with the quotient identities. So the fact that tangent is equal to sine over cosine and cotangent is equal to cosine over sine. So you can rewrite, like if you wanted to graph tangent on your calculator, you could type in tangent, but you could also type in sine over cosine and it would graph the same function. And for example, whenever I derive the derivative in calculus, when I derive the derivative of tangent, or like if I forget what the derivative of tangent is, I use sine over cosine because sine over cosine are much easier derivatives to know. So it's very important to know these fundamental identities that are helpful to us in rewriting expressions or functions or equations. They're also often used in different derivations. Now, the Pythagorean identities are the identities that are new to you today. And there are three different identities, and you're like, oh man, those look kind of complicated. How am I going to memorize those? The thing is, you really only have to memorize this first one. And then the other two can easily be derived from this first one. And I want to make sure you understand where this first identity, sine squared plus cosine squared equals to 1, I want to make sure you understand where that comes from and why it's referred to as a Pythagorean identities. When you see Pythagorean, what do you think of? Like what pops up into your head when you see the name Pythagoras or Pythagorean?
Right triangles.
Right triangles, and specifically
a squared plus b squared equals c squared.
Right, the relationship between the sides of a right triangle, which we call the Pythagorean theorem, right? The handy dandy Pythagorean theorem. So thinking back to our unit circle, am I going to be able to fit my circle here? Okay, so this is a unit circle, meaning this point would be 1, 0. This would be 0, 1, negative 1, 0, 0, negative 1. Okay. And if I were to pick a point on the unit circle, I'll just pick a point from quadrant 1 for simplicity. That point, you guys know, can be described as cosine of theta, right? Where this is the angle theta, cosine theta, comma, sine theta. Right? This is how we use the unit circle as a reference for us to evaluate trig functions for angles that lie on the unit circle. But it's true, the relationship is true for any point, and there are infinitely many points, which is so crazy to think about, right? There are infinitely many points that lie on a circle. And for every single point, that point can be represented as cosine of theta for the angle that's in standard position, and comma sine of theta. Now, if we were to create a right triangle, since we're in quadrant 1, so by dropping perpendicular there, making a right triangle, that would mean this side would be cosine theta, this side would be sine theta, And it's a unit circle, right? So let's use orange still. So this side would be 1. So I want to pause right there and make sure, does anyone have questions about the picture that I just drew? The right triangle that I just constructed inside the unit circle? Now, Rye mentioned the Pythagorean theorem, the relationship between the sides of a right triangle, a squared plus b squared equals c squared, where a and b are the legs of the right triangle, and then c represents the hypotenuse. So if we use Pythagorean theorem here, where we take a leg and square it, the other leg and square it and set it equal to the hypotenuse squared, well, we could write that as cosine theta squared plus sine theta squared equals to 1 squared, which you guys know that that notation kind of simplified to the notation that we use for exponents with the trig function. Functions can be written as cosine squared, theta plus sine squared theta equals to 1. These are the same thing. Remember, the theta is it's just a variable, right? You could think of any variable. So the way that I have it written up here is where the input is x, but it could also be theta. It doesn't matter. It could be beta. It could be, I don't know, z. Doesn't matter. So sine squared plus cosine squared, or cosine squared plus sine squared, doesn't matter the order because addition is commutative, is always equal to 1. If you can remember that Pythagorean theorem, the other two are super easy to figure out. I actually don't even really have the other two memorized. Like, I know they exist, but in my head, I always think about deriving them. The second Pythagorean theorem can be derived by dividing each side of the first Pythagorean theorem by cosine squared. So if we thought about dividing sine squared, I don't know if it would be helpful for me to write this out. Let me add a page just so I can. Okay, so if I take sine squared plus cosine squared equals to 1 and divide each side by cosine squared, and then simplify, well, since sine over cosine is tangent, sine squared over cosine squared is going to be tan squared. Cosine squared over cosine squared, well, that's just 1. And since 1 over cosine is secant, 1 over cosine squared would be secant squared. So that's where we get the second Pythagorean identity. Any ideas for how we could derive the third Pythagorean identity?
You divide by is it sine squared?
Divide by sine squared on each side. So I'm dividing by sine squared on each side of the equation. So then I have 1 plus, well, cosine squared over sine squared, since cosine over sine is cotangent, will be cotangent squared. And then since 1 over sine is cosecant, 1 over sine squared will be cosecant squared. Does anyone have any questions on the Pythagorean identities? And you'll see that for the fundamental identities, so like the Pythagorean theorem, the Pythagorean identities are considered fundamental identities. You are allowed to kind of change things around. And like I could rewrite the second Pythagorean identity as 1 equals to secant squared minus tan squared, like where I think about subtracting tan squared from both sides. So we're allowed to use properties of equality to manipulate the fundamental identities. But you'll see once we actually start verifying identities, there are a set of rules that we'll have to follow. Think of it just as like game rules or rules for a puzzle. Where you will not be able to use properties of equality, but you can for the fundamental identities you use. Okay, this last set of identities in this section, last set of fundamental identities in this section are the even odd identities, which you already know, right? We've talked about all of these. So I have all the odd identities stated and then all of the even identities stated. So we're going to start by simplifying trig expressions using identities. One strategy for simplifying trig expressions, if you don't see any other identities, like if no other fundamental identities are popping out to you, one strategy you can always fall back on is to change everything to be in terms of sine and cosine. Because all of the trig functions can be written in terms of sine and cosine, right? Tangent can be written as sine over cosine, cotangent can be cosine over sine, and then you have your reciprocal identities. So here's the first expression that we're going to try and simplify. And this is an expression. So we're going to state that it's equal to something, but we are not solving. Expressions you can simplify, you can rewrite, but you are not solving anything. We're actually not solving anything in this section. No solving equations. We are simplifying these expressions and then we are going to verify identities. So looking at this expression, there's a sine and a cosine in there, but there's also a cotangent. I don't see like any Pythagorean identity that I could use. Even odd identities wouldn't really apply here. But we could rewrite cotangent in terms of sine and cosine, right? We could replace cotangent with cosine over sine. And then to simplify that a bit, well, that's going to be cosine squared over sine plus sine. Well, that doesn't really look any simpler. But oftentimes, if we're trying to go simpler and we have a sum, especially a sum that has a fraction in it, it can be helpful to get a common denominator. So since this second term here is sine over 1, you can think of it as sine over 1. We could get a common denominator by thinking about multiplying by sine over sine, which is just a version of 1. That gives us a common denominator of sine. And our numerator would be cosine squared plus sine squared. Does anything stick out to anyone for what we could do next?
Wait. Actually, no. Wait, wait, don't you also have, wait, never mind. Oh, sine squared over, actually, sorry.
Do the signs
Love the
cancel?
sign.
Say that one more time.
Wait, me or
Yeah, Lucas, what did you say?
do the signs cancel?
No, you can't cancel across, and we would be right back where we were before. You can't cancel across
Yeah.
a difference. Rye, did you say something?
No, I said the same thing as Lucas.
Okay. You guys focus on the numerator. What can that simplify to?
1.
1.
Yeah.
Pythagorean identity. That's just 1. And then Oscar, how can we rewrite 1 over sine?
That's cosecant x.
Can't. Isn't that crazy, you guys? That can simplify that down to just cosecant, that like more complicated expression can simplify down and just be equal to cosecant. Like if you wanted to graph cosecant on your calculator, you could type that in, but you could also type that crazy expression in for the function. It would graph the same thing. It's craziness.
Okay.
All right. Let's give this next one a go. Let's do a new color. Feeling green. Okay. 1 over cosine squared minus 1. Does anyone have any ideas? Oscar.
1 over cosine squared is just secant squared.
It is. Okay, let's go with this. We'll go with this. Secant squared. Okay, so we can rewrite that 1 over cosine squared as secant squared.
Can't you also first like use what we did before, like use like common denominator?
Yeah, that's what I initially thought, but actually, so we'll write out both, but let's go with what Oscar's idea was because it's actually more efficient than getting a common denominator. But getting a common denominator is totally reasonable as well.
Mhm.
So secant squared minus 1. We have an identity that has a 1 and a secant squared in it. And if we go back up to our handy dandy Pythagorean identities, remember how I said that for the fundamental identities, we're allowed to think about using properties of equality to manipulate them?
Mm-hmm.
So we right now have secant squared minus 1, and thinking of the Pythagorean identities, secant squared minus 1 is actually equal to
10.
Tangent squared.
tangent squared. Which is really as simplified as you can get. Now, if we used Janet's idea of getting a common denominator, which is totally reasonable. Here, I'm gonna I'm going to copy this and paste it over here. So to get a common denominator, right, we would think about multiplying the 1 by cosine squared over cosine squared. So just to write that in multiple steps, which you wouldn't have to write necessarily in multiple steps. So I'm thinking about multiplying that 1 by cosine squared over cosine squared. So then as a single fraction, that's 1 minus cosine squared over cosine squared. You still have to think Pythagorean identities. So the numerator, you could be like, hey, there's a 1 and a cosine squared in there. That kind of reminds me of that first Pythagorean identity. If I scroll back up there. Right? 1 minus cosine squared, we could get from subtracting cosine squared from each side of that first identity. So sine squared is equal to 1 minus cosine squared. So I can actually replace 1 minus cosine squared with sine squared. And then sine squared over cosine squared is?
Tan squared.
Tan squared. I'll tell you guys, for the identities test, I don't even make a key. I assign like how many points I make each problem. I usually make like each verifying 1 out of 10. Because I swear you guys come up with like new ways of verifying or like using different identities. There's different approaches you can use and it's based on what you see. So like, I don't even try and make my own key because it's very unlikely that you would actually follow the same steps that I would follow. So just kind of an interesting, I think it's a cool part of this section. Okay, so that was kind of, those 2 examples were kind of our warm up leading into the verifying identities, which is the fun part. Like solving a puzzle. How are we all doing, you guys? Hanging in there? Are you able to do, I saw in the 10th grade thing yesterday, everyone was using their, you all know how to use your little response things. How are we feeling? Use a little reaction. Am I able to do that too? No? I don't know if I can do it. Okay. All right, thank you guys. Okay, so now we're getting to the good part.
Okay.
Verifying identities. Okay, so we're going to be using the fundamental identities that we have listed above, all the ones you're familiar with already, and the Pythagorean identities, to verify these other identities. So you have to remember that the equations that you're given that they are identities, that the left-hand side equals to the right side, and you need to prove it. So it needs to be, you can't just go like, oh yeah, I see it. Left-hand side is equal to the right-hand side and assume that it's obvious. That's not the point of these. You are literally given that the left-hand side equals to the right-hand side. You need to make sense of it to yourself and to me or whoever you're trying to communicate to, that they are actually equal to each other. So some tips and tricks. I like to usually start with the more complicated side of the equation. The truth is, since the left-hand side equals to the right-hand side, you could use either. Sometimes both sides look complicated. I have a bunch of different examples, and I'll let you know what my strategies would be. But I mean, the truth is you could work either side and it should work. It can also be helpful to combine all sums and differences of fractions into a single fraction. I mentioned that before. As kind of a fallback, you can always convert everything to sines and cosines. So given you're using the fundamental trig identities. You can use algebraic techniques to manipulate one side of the equation until the other side is achieved. So that includes like getting a common denominator, multiplying by a version of 1. You cannot use properties of equality. You can't move one thing to the other side. You can't multiply both sides of the equation by something. You are choosing one side to work on, and you are only manipulating that side. If you get completely stuck, you can start over and maybe start on the other side, but you cannot work both sides. The only time you are allowed to use properties of equality are whenever you are manipulating the fundamental identities, which are the reciprocal, the quotient, the Pythagorean, the even odd. Does anyone have any questions for me before we begin? Okay. So, looking at this equation, which side looks more complicated to you guys?
The left side.
Yeah, I think the left side. Again, you can work either side, but I think it's going to be easier, especially since the left side is in terms of tangent and cotangent, and the right-hand side is in terms of sine and cosine, and you know you can always fall back on changing everything to be in terms of sine and cosine. I would probably work the left-hand side. Please pay attention to how I'm showing work because I'm expecting you to do this too. So if we're going to work the left-hand side, you're trying to keep your equal signs as lined up as possible in the center. Like if you wanted to draw a straight line going down the center too, you could to help you line them up. You don't have to do that, but I'm only working on the left-hand side. On the left side, no identities except for the quotient identities stick out to me, like changing tangent and cotangent to be in terms of sine and cosine. So that's what I'm going to do first. I'm going to rewrite each of the tangents as sine over cosine, and each of the cotangents as cosine over sine. Okay. Now from here, well, the right-hand side is a difference of 2 squares. The left-hand side, we still have this big fraction, and we also have complex fractions now. There's no complex fractions on the right-hand side. You want to keep checking the side that you're trying to get the other side to match, like the side you're working on to match. So I want to get rid of those complex fractions, the fractions that are in the numerator and in the denominator. So I can think about a version of 1 that I want to multiply the left-hand side by in order to get those complex fractions to cancel. And looking at the denominators of the complex fractions, When I say complex fractions, does everyone understand what I'm referring to?
Mm-hmm. What? Yeah.
So since cosine and sine are the denominators of those complex fractions, I'm going to multiply by cosine times sine over itself. And I always like to draw, whenever I'm trying to get rid of complex fractions, I always like to draw the grouping symbols around the numerator and denominator to help me remember that I'm distributing, right? Like I'm going to distribute cosine times sine to the first fraction and then the second fraction in the numerator and the denominator. Okay, so when we multiply sine over cosine by cosine times sine, cosines will cancel and we'll be left with sine squared. Then when we distribute to cosine over sine, the sines will cancel and we'll be left with minus cosine squared. And in the denominator, when we distribute to sine over cosine, cosines cancel, we'll be left with sine squared. And then distributing to the cosine over sine, the sines cancel and we're left with plus cosine squared. So we're almost there, right, you guys?
Mm-hmm.
The numerator is hey, that's it. And then right away, you should see sine squared plus cosine squared. What's that equal to?
1.
So this is just sine squared minus cosine squared. Yeah. And if I were working the right-hand side instead, all of my work would be on the right-hand side. So this is what I meant by if you want to draw like a line to like separate the sides, you can. It's up to you. That looks kind of funky on mine.
I'm just wondering, but like, can you show how you would like do it from the right side? Like, or is it?
It would be something like figuring out like how to multiply by a version of 1 that's kind of crazy. So no, I'm not going to take the time to do it. There are some that it's a little bit more obvious. It can be done, but like you wouldn't
Yeah.
work that side.
Okay.
Okay, let's do, I get it. We've been here for a long time. Let's do one more together, and then I'm going to have you guys try one in breakout rooms, and then I'm going to let you guys go.
Mm-hmm.
Because we've been here for a while. So looking at this equation, are we all in agreement that the left-hand side is more complicated looking?
Mm-hmm.
Yes?
Yeah.
Now, 2 secant, I mean, there's always, you could change to be in terms of sine and cosine, but that's another one you would end up having to like figure out how to split it up into 2 fractions. It would just, it wouldn't be what we're trying to go for. Like when we use identities, when you use identities down the line, it's going to be to make something more simpler. So that's kind of what the strategy should be for these verifying identities. Now on the left-hand side, we have a sum of 2 fractions. No other identities really stick out to me. Everything's already in terms of sine and cosine. So I would probably get a common denominator.
Mm-hmm.
And we could get a common denominator by multiplying the first fraction by 1 minus sine over 1 minus sine. And we can multiply the second fraction by cosine over cosine. So that would give us 1 minus sine squared, like the quantity 1 minus sine all squared, plus cosine squared in the numerator over 1 minus sine times cosine. Does anyone have any questions on how I got to there? Okay, we need to multiply out the numerator and then combine like terms if possible. Please don't say that 1 minus sine, that quantity squared is 1 minus sine squared. Remember, that is 1, and I'm going to write it out just to emphasize that. That's 1 minus sine times 1 minus sine. That exponent refers to repeated multiplication. I'm going straight. So then when I multiply out, I'm going to add a page. When I multiply out that product, I'm going to get 1 minus 2 sine plus sine squared plus cosine squared. Nothing's happened to the denominator yet. Sally, does anything call out to you for what we could do next?
I don't really know. No.
What about you, James? Does anything call out to you?
I'm not sure.
Oh,
Um,
Rye, do you see anything?
No.
I
Lucas? I'm just going up the list.
I don't know. Maybe the bottom, the denominator, where it's 1 minus sine x times cosine x. Actually, maybe not. Or maybe in the top where it's sine x squared plus cosine, or sine squared of x plus cosine squared of x. That's equal to 1.
That's equal to 1. Sine squared plus cosine squared is equal to 1. So then if we combine like terms in the numerator, that's 2 minus 2 times sine. You might be able to see where we're going with this, right? Like keep an eye on what we're trying to get to. We're trying to get to 2 times secant. I have a 2 now in the numerator. That's helpful. So if we think of 2 as the GCF of the numerator, we can factor that 2 out. And then Woohoo! Best part when you get to cancel in the numerator and denominator. And the reason we're allowed to cancel is that's 2 times the quantity 1 minus sine. And 1 minus sine times cosine. You can cancel across multiplication. So that leaves us with 2 over cosine, which is 2 secant. So here's what I want to do for the next one. I'm going to throw you guys into breakout rooms and see if you guys can talk to each other to figure out how to verify the next one. Hint, I'd work the left-hand side. Do I have to pause the recording? Yeah, I can pause the recording.